All right, so this is our final inequalities lecture. We'll cover um, Cauchy, Schwarz, and Holder, and we'll cover Jensen. Okay, but yeah, so what's the idea behind all these problems? So last 2 weeks we talked about some kind of brute force technique where you see an inequality, you expand it, you homogenize it, and you have some big symmetric polynomial or maybe cyclic polynomial. Um, Today I want to talk about when that doesn't work, like when that becomes infeasible. So for example, if you have an inequality like this, oops, you can imagine trying to expand it, but because of the roots, you'll in order to get a polynomial, you'll have to cube it twice. Like if you cube it once, you'll still have a leftover term, and you have to. So the point is, you'll get a very, very big thing if you just try to brute force this. So there's a lot of problems where you have to know some techniques that aren't brute force. And yeah, so let's talk about that. And okay, so the first thing I want to cover actually is the power mean inequality. It's related to all these things, but so let's see what it says. Um, Otherwise, do you guys know this inequality from before? Have you guys seen it before?
Yes, where we drive AMGM from.
Yeah, okay. It's some generalization. But yeah, the idea is just, if you have A1 through AN and then you have R greater than S, then uh, this um, this is called the Rth power mean. So if R is 1, you get just the arithmetic mean. If R is 2, you get the square mean and so on. And the point is this is going to be, um, there's an inequality. If R is greater than S, then you have this. So I'm going over this quickly because I hope you guys have all seen this before. Yeah. So please tell me if you haven't seen this inequality. Um, okay, great. So um, yeah. So can you tell me what the weighted version of this inequality should be? Like just how AMGM has a weighted version, this also has a weighted version.
Yeah, assuming we have n weights, which sum is equal to 1, W1 plus W2, etc. is equal to 1, would be W1 A1 to the power of R plus W2 A2 to the power of R, and so on, all to the power of 1 over R.
Yeah, great. So it's just you just wait. The weights just go here. Okay. And in most applications you'll have to know the weighted version. Okay, so that's that.
I think that in the denominator we should have R instead of N
Ah,
and S instead of N.
in general or for the unweighted version?
Because the definition of this mean of the power
Ah,
mean.
oh, sorry. Okay, you're okay. So now you point out your point. There's actually a typo here. I've read this should say N, not R. Okay, yeah, so actually I have the wrong thing written. It should be N. So okay, thank you for mentioning. I didn't even notice that in my notes. So thanks, Karam. It should really be N. And what does it mean? It means we're taking the mean of the rth powers to the power of 1 over R. Okay, so um like when R equals 1, this is just A1 plus AN over N. Like it's just the arithmetic mean. Yeah, so it should be N, not R. And like if R equals 2, it's you take the squares and then you divide by N and then you take the square root. Does it make sense, Karan?
Yes.
Yeah. Okay, so it's like this. Um, and the other reason you know it should be N is because think about the equality case, right? When I plug in here, so if I plug in all of them are equal, A1 equals A2 equals AN, if they're all equal, well, okay, if all my numbers are equal, no matter which mean I take, it should just be that number, right? So if they're all equal to some number A, arithmetic mean, geometric mean, harmonic mean, no matter how you take the mean, you should get A. So, and that's what happens here, right? Because I'll get n times a to the r divided by n, so I'll get a to the r to the 1 over r. Yeah, so it should really be n. Okay. And great. And in the weighted version, since it is weights, you just you don't have a denominator. Yeah. So does it make sense? What is it? Okay. Great. So now let's do a problem. So we talked about the weighted version. I've written it here. So yeah. Great. So now here we have this problem. And I claim this is a problem you should solve using weighted power mean. So okay, I'll make an observation here, which is this here is the r equals 1 power mean. This is the r equals 0, or the geometric power mean, and this is the r equals 3 power mean. So this inequality, it's about like comparing like a sum of 2 power means to this one. Yeah, okay. So any comments how you should start this problem?
Since we have an 8 on one side, we can take the weights 8 over 9 and 1 over 9.
Okay, so you're suggesting we use but what r are we using? Like what powers are we comparing for weighted power mean? Like what are r
1
and s?
and 1 over 3.
Okay, great. So yeah, the point is these numbers, you know, they actually have nothing to do with how you solve the problem. Okay, so the way you solve this problem is you understand that, okay, what's the problem? The problem is this cube roots, and I want to get rid of these cube roots. So the way that I get rid of these cube roots is I interpret the right-hand side, right? I say this is equal to, it's like this. It's ABC to the 1/3 plus A cubed, B cubed, C cubed to the 1/3. Okay, so times some constants. Okay, so it's like I'm doing power mean with x1 is ABC and x2 is A cubed plus B cubed plus C cubed. Like so like the idea is to look at this and say, look, I don't know how to deal with these cube roots, but I can express this as some kind of weighted mean using these terms. And then the inequality should be that, okay, whatever's on the right-hand side should be less than or equal to. Now I just take, yeah, so that this is equal to, this is r equals 1/3, and I can compare it to r equals 1, because with r equals 1, I'll just have, what? I'll get rid of the cube roots. So okay, let's write it out. So so let's write it. We'll have some constant, I don't know, times ABC to the 1/3 plus some other constant, I don't know. Is A cubed plus B cubed plus C cubed to the 1/3. Okay, sorry. Okay. Need some more space. So let's maybe go here. So I'll have like this to the 1/3 and this cubed. So this is the r equals 1/3 power mean, and I'll compare it here to just the regular r equals 1. So this will be some weight times ABC plus some weight is a cubed plus b cubed plus c cubed. Right. So, why does this help us? It helps us because, okay, if we have to figure out what the weights are, but it helps us because this inequality is the same thing as, let's write 27a plus b plus c cubed is greater than or equal to this, what? 8 cube root of abc plus cube root of a cubed plus b cubed plus c cubed over 3 cubed. So the point is, if we can show this is bigger than or equal to this, then we're done. But these have no cube roots. Yeah. So the point is, you replace this sort of thing that has cube roots with these two, which now there's no, it's just a polynomial. Does the idea make sense? Okay, maybe okay. Okay, maybe I'll say I've made a mistake here. You guys understand what the mistake here is?
We should take a cubed plus b cubed plus c cubed over 3, not b cubed plus b cubed plus c cubed.
Where? You mean here or here?
Yeah, it should be over 3 as well.
Yeah, it's over 3. That's right. So there's a mistake here because, yeah, so why why do I have to put over 3 here?
Because it's under the cube root, and our point is to take
Well, no, but
r is equal to 1 to get rid of it.
Well, no, but the point is you can like, we could have not done that and just changed the weight, right? Why do we need to have like, why do we have to have it, instead you could say, okay, I'll just do a cubed plus b cubed plus c cubed, and I'll change the weight. Okay, maybe I'll come back to this in a moment. So let's just, okay, let's sort of just write the full solution and then we'll discuss it. So, okay, the point is, okay, in order for this to work, the weights should be 8/9 and 1/9, right? So, yeah, so we put here, so we write W1 is 8/9 and W2 is 1/9. Okay. So now what's the inequality? So it's like this. Okay, so here we have basically the right-hand side, and here we have what? So now we want to say that yeah, so if we want to complete the inequality, we should show now that this one is bigger than or equal to a plus b plus c over 3 to the power of 3, right? Because we take yeah, so we take this, we divide by 9, and then we cube it, right? Yeah. So Yeah, and this inequality should be, how do we prove this? So, okay. This inequality is then equal to a plus b plus c cubed is bigger than or equal to, we multiply by 27, so 24 abc plus a cubed plus b cubed plus c cubed. But this is just true, right? Because when you expand, the a cube, b cube, c cube will cancel, and what you'll have left is something like a squared b compared to abc, and it just majorizes. Yeah, does it make sense? Yeah, I can't tell if yeah, hello.
But when we have some inequality, how could we decide what is the technique that we should choose to solve or to prove?
Yeah, so maybe that's what I was trying to explain before. Maybe I should just give them the solution first. So the reason I know to use power mean here, or one reason, is because of these cube roots, right? So like that's why I was trying to, like, when I see this expression, you can interpret it as it's a power mean with weight with exponent 1/3, right? Like let's write like here's what I'm trying to say. I'm trying to say that, okay, maybe I was trying to like write x equals abc and y equals a cubed plus b cubed plus c cubed over 3. Okay, then the right hand side is basically what it's 8 times x to the 1/3 plus y to the 1/3. Okay, but what is this? This is like if I wrote 8/9 x to the 1/3 plus 1/9 y to the 1/3, the power of 3. So if I have this expression, this is a power mean of x and y. So the right hand side is basically a power mean of x and y. I mean, it's changed, there's some constant 1/9 and there's this exponent, but that doesn't really matter. Do you see what I'm saying? Like if I can use an inequality to bound this, then it'll help me bound this. Does it make sense, Karen? Can you hear me all right, Karen?
Yeah.
Yeah, so does the explanation make sense why we decided to use power mean here?
Yeah, because we want to get rid of the cubic root.
Yeah, the cubic root, exactly, yeah. Okay, but there's one other point I wanted to make, which is why did we use ABC and a cubed b cubed plus c cubed over 3? Because you can also imagine, what if we use something like we used ABC and y is a cubed plus b cubed plus c cubed, right? Like you can try, okay, now I'll write 8 times abc to the 1/3 plus I can pull out this constant, right? And okay, you can do this. And you can try to use power mean on that. So you can try to say, okay, well, this is less than or equal to some kind of something, right? But this won't work. And the reason it won't work is because what's the equality case for power mean? It's when all of the variables are equal. if I make these equal, it's not the correct equality condition. Like the correct equality condition is A equals B equals C, right? And that will happen when these are equal, but not when these are equal. Does it make sense what I'm saying?
Yeah.
So like whenever you use an inequality, you have to make sure you have the correct equality case. Otherwise, it will never work. So like if I try to start like this will never lead to a solution because the equality case is wrong.
And maybe because the weight actually could you go over it again?
So what I'm saying,
last
yeah, what I'm saying is you can try to make a solution like this, right? Because I can make the weights like, I can, these are just numbers, right? I can make the weights like 8 over the sum and this over, like I can do that, right? Like I can make the weights W1 equals 8 over 8 plus cube root of 1/3. W2 equals cube root of 1/3 over, like this, right? It's not natural, but you can do it. It will never work because whatever inequality you write down, the equality case would be the equality would be ABC equals A cubed plus B cubed plus C cubed. But that's the wrong equality case, right? Because this isn't true when A equals B equals C. So you have to use this. Does it make sense?
Yes, but how did we know that the equality case in the original inequality holds if and only if ABC
Okay.
equal?
So
Yeah.
so we don't know if it's only if, but we know if. We know the equality holds if A equals B equals C. Right? In here, right? Because you should whenever you see an equality, you should check the equality. Okay, so if I have A equals B equals C, then I have what 9, 8, and 3, right? So and 1, right? So 9 equals 8 plus 1. Yeah. So it works. If A equals B equals C, you have equality. So in this one, if A equals B equals C, I don't have equality. So in the end, you want to prove your thing by a chain of inequalities. So if this one has equality at A equals B equals C, each of these also has to have equality at A equals B equals C. Does it make sense?
Yeah.
Okay. So that's why, any idea like this where you use, ABC, this cannot work. You have to have the correct normalization. Okay.
But why is the one we wrote not equal at A equals B equals C?
This one here?
Yeah, we didn't finish it. How do we know?
Yeah, so first let's see what would the inequality be, right? So if we wanted to write it like this, right, what would be the inequality? So let's do it. Let me copy this over. Okay, so I copy this maybe to another page or something. Yeah, so let's see. Oops. Okay, so imagine we try to work with this inequality, right? So we're trying to do power mean for r equals 1/3 and r equals, say, 1, where these are the two things. Well, what would happen is you would have some constant or some weight times ABC plus some other weight times A cubed plus B cubed plus C cubed. Okay. But what would be the equality case here? Equality, if and only if ABC equals A cubed plus B cubed plus C cubed, right? Because that's what we did here. So whatever inequality you write down, it's going to be too weak for you to use it because it doesn't even have equality at A equals B equals C. Does it make sense, Abdullah?
But can't we modify the way to account for this?
no, you have to modify this term, not the weight. You see? The weight, okay, it's like this. What are we trying to do? We're trying to, yeah, so what's the goal? So the goal is we have this term, 8 cube root of ABC plus cube root of A cubed plus B cubed plus C cubed over 3, okay? And we want to, the goal is to upper bound this. So the technique that works is to use power mean on x1 equals ABC and y and x2 equals A cubed plus B cubed plus C cubed over 3. But what doesn't work, so this is not going to work, is if you use power mean on x1 is ABC and x2 is A cubed plus B cubed plus C cubed, right? Because okay, you can modify the weight to get this. So what we can say is, okay, we can say 8 over 8 plus cube root of 1 over 3 times cube root of ABC plus cube root of 1 over 3 divided by 8 plus cube root of 1 over 3 times cube root of A plus B plus C, A cubed plus B cubed plus C cubed. Yeah. So Abdullah, this is what you mean by modify the weight, right?
Like just like taking a factor of 1 over square root of 3 and then
Yeah, so that's what
Yeah.
you're taking yeah, it's like this, right?
yeah, well, almost, yeah.
Because you want to get 1 over cube root of ABC, right? So I have to pull
I was
that.
just thinking of taking a factor of 1 over the cube root of 3 from weight 2.
Yeah, so you're putting this into the weight, right? Is what I mean? Is what you mean, I think, right?
Yeah.
Yeah, so I can do that, and what you'll get is a valid inequality. You'll get something correct because then, okay, I can say power mean says if I take this to the power of now 3, I can compare it to okay, let's just write this is weight 1, this is weight 2. I can write it as weight 1 times ABC plus weight 2 times A cubed plus B cubed plus C cubed. Okay, you can do that, but what I claim is that when you go and because at the end, you have to what? You have to compare what you get here. You have to compare it to this guy, right? To 3A plus B plus C.
Yeah.
So at the end, this one needs to be compared to some constant times A plus B plus C. And what I claim is maybe cubed, right? Because we cubed here, so we have to cube here, right? So my claim is if you do it like this way, you won't be like this, you won't be able to compare these guys. Like this, the inequality here is going to be false.
I see.
And the reason I knew it was going to be false from the very beginning is because when I do this, I know this is the wrong thing to do. Because if I do this, then the power mean equality case will be when these are equal. But that doesn't even include the equality case of the original inequality.
I see.
Like,
I see.
does it make sense what I'm saying?
Yeah, okay.
Like if I'm trying to take an inequality, I break it up into steps. The equality case for each step should include the original equality case.
Yeah.
So this idea was broken from the beginning. But this one is okay. So I don't know if it'll work, but at least there's a chance that this works.
I see.
Does it make sense?
Yeah, it makes sense.
So this analysis here of like the equality case is an extremely important thing because otherwise, it's too hard to play around with the weights and know like what the correct thing is. It's really, really hard. Always make sure that whatever you're doing respects the equality case. That's a much better way to decide than like, figuring out, do I do A cubed plus B cubed plus C cubed over 3 or, it's too hard to tell. Okay, All right, so great. So now let's look at
I have a question about the mean power, the power of inequality. Does it follows when R is bigger than S, or S is bigger than, or S is bigger than R?
What do you mean? I mean, there's two. Like, if R is bigger than S, then the Rth power mean is bigger than the Sth power mean.
Yes, that is what I mean.
Oh, are you asking the direction? Like, which direction it goes?
Yes, because here 1 is less than 3, and the power mean of
No,
the
it's the right-hand side is the 1/3 power mean. Let's be very careful here. So here we have the R equals 1 on the left-hand side. On the right-hand side, we have R equals 1/3. Because we're taking the 1/3 powers, and then at the end, we're taking the 1/3 root, which is the third power.
okay, I see. So it's the 1/3 power mean.
Yeah. Yep. Exactly.
Yeah.
And we want to use the 1/3 power mean because there's cube roots here. Yeah. Does it
Okay.
make sense?
Yes.
Yeah. Okay. Good. Okay. Yeah. So power mean is one very, very strong tool for getting rid of powers. And no, okay. Yeah. And yeah. Okay. Yeah. I'll say more later. Okay. Okay. So now let's talk about holder. So holder is Cauchy, Schwarz, and Holder are related. Holder is basically the strongest inequality there that exists for Olympiad mathematics. Like it's just it can do miraculous things. So let's look at the statement of Holder. Yeah, but actually I don't exactly write like the way that I phrased it here. I think there's no, actually no, this is okay. This is an okay way to do it. Okay. Yeah, so let's copy the statement and then I'll give the proof. So okay. Sorry, I'm adding a page to the document. Okay. All right, so this is the statement of Holder's inequality. Yeah. So Holder's inequality has two sets of variables, A1 through AN and B1 through BN. Okay, so it's not like AMGM. AMGM there's just A1 through AN. Now there's two sets. And we have to choose well, okay, first let's consider the case where P and Q are 1/2. Okay. So in this case, this inequality is saying that A1 plus all the way AN to the power of 1/2, B1 BN to the power of 1/2 is greater than or equal to A1 to the 1/2. Let's write square root actually. I think it's a little more natural. So square root of A1 B1 plus all the way square root of AN BN. Okay, it's like this. So this version, when P and Q are as a half, is called Cauchy-Schwarz. Okay. And the general version is something like, okay, you can have weight, so you can do like AN to the 1/3, and then B1 BN to the 2/3 is greater than or equal to this A1 to the 1/3, B1 to the 2/3 plus AN to the 1/3, BN to the 2/3. Okay. And so yeah, so there are some like weights you have to pick that add to 1. So before we prove holder, let's make an observation about homogeneity. So AMGM is homogeneous in the sense that if you scale like all the variables, like both sides don't change. So this is also homogeneous. But it's homogeneous in A and B independently. So if I change each AI and I scale it by R times AI, then both the left-hand side and the right-hand side multiply by R. Does it make sense? Like what I'm saying, I'm not saying scale all the variables, just scale the A variables, then both sides will scale by the same by I guess R to the 1/3. Does it make sense what I'm saying? All right, so if you scale A's by R, both sides scale by R to the P. Does the statement make sense?
Yeah.
Yes.
Okay. And similar for the B's. If you scale the B's, so if you scale the B's by R, then it changes by B to the Q. Okay. So it's like, we could call it bihomogeneous. It's homogeneous in two sets of variables. So this is very important for the proof because it means that if I want to prove holder, you can assume without loss of generality that both sets of variables sum to 1. Okay, because if they don't sum to 1, just scale them both so they sum to 1, and the inequality will be the same, right? Both sides will just scale. Does it make sense? Why I can
Yeah.
assume without loss of generality that both.
Yeah.
Okay, so this is very important, right? So okay, so now the proof actually is it's not hard. It's kind of because now, okay, now what? Now we just do point is now it just follows from AMGM actually. Because what's the situation? So the situation is we have two sets of variables, both of these sum to 1, right? So we just want to show that this 1 is greater than or equal to A1 to the P, B1 to the P plus ... AN to the P, BN to the Q. Sorry, like this, right? This is what we want to show. But it's true because we just use weighted AMGM, right? So AI to the P, BI to the Q for each one is less than PAI plus QBI, right? This is just weighted AMGM with weights P and Q. So now if I sum these up, if I sum like I equals 1 to n, I'll have here A1 plus AN times P plus B1 BN times Q. And here I'll have the right-hand side. I'll have A1 to the P, B1 to the Q, plus ... plus AN to the P, BN to the Q. But of course, these are both 1 by assumption. So this is equal to P plus Q, which is 1. And that proves the inequality. Does it make sense, the proof?
Yeah.
So now I have to ask, what's the equality case? Right? So we proved this inequality as by summing a bunch of inequalities. So the equality case should be when all these equality cases hold. So when is that true?
When for all I, A sub I equal B sub I.
Okay, great. So the equality case here equality case AI equals BI. Okay. So in particular, like, you know, the A's can all be different from each other, and the B's can all be different from each other. We just need them to be equal. But now I'll say one thing. The quality of this is a little bit more than the quality of this. But I'm saying, okay, so if all the AI and all the BI are the same, okay, great, the inequality is true. But it's true in a little bit more generality because you see, what is the first thing we did? We scaled them. So the equality should be that after you scale them, all the AIs equal all the BIs. So the actual equality case is if and only if the ratio of the two collections is the same. You guys know what I mean by this notation here?
Yeah.
Yes.
So for example, like if I have 1, 2, 3 for A1, B1, B2, so yeah, this is for A's, and then for B's I have like 2, 4, 6. That's also going to give you equality. Because after I scale them, because the first thing we did is we scaled them, we're going to have AI equals BI. Does it make sense what I'm saying?
Yeah.
So the equality case is yeah, maybe I write it down. It's not actually AI equals BI, it's A1 over B1 equals A2 over B2 equals ... equals AN over BN. The ratio between all of them should be the same. That's the full equality case. And you can see if that's true, then this inequality is true. Okay. So any questions? Okay. So that's the proof of Holder. So let's look at some problems that use Holder. So yeah, let's start with this one. Right. Right, so this is our inequality. And let's just remind ourselves what Holder says. So Holder says that A1 to A1 plus AN to the P, B1, BN to the P is, sorry, to the Q. That's we need weights. Is greater than or equal to A1 to the P, B1 to the Q, AN to the P, BN to the Q, like this, where P plus Q equals 1. Okay.
We write the cyclic sum of the left-hand side squared multiplied by the cyclic sum of B
so
plus
actually,
C.
I don't want to square it. You can, it's equivalent, but I want to keep it in this form. So I won't square. It's really equivalent, but I won't square it because I want. Well, okay, I want so. But let me just first say what we're trying to do. What we're trying to do is we're trying to match this term with A, and this term with the right-hand side. That's what we're trying to do. So we want like this one to be like A1 plus AN, and then this one to be like A1 to the P, B1 to the Q, like this. Not exactly. There will be some exponents you have to work with, but we want like that. So yeah, so we want to use holder in the following form. To the power of p. We'll decide what p is. And then here we want, I don't know what to put here. This is sort of the magic of holder. Like you have to guess one of the terms. It's never clear. And something goes here, right? So what goes here, we'll have a over square root of b plus c to the power of, I won't write the whole thing because it's long, so I'll write, we want a cyclic sum of a over square root of b plus c to the power of p times whatever question mark is to the power of q. And okay. So the idea is I won't worry about the square root. Only thing I want is I want to make sure that the term I get here really is a plus b plus c. Okay, because if it's not a plus b plus c, then I don't know, it's really not possible to do what I want to do. So I really want to see here a plus b plus c. Okay, so yeah, what do I want? So I want this as a plus b plus c. And the other thing I want is I want this is easy. So what I mean is here I have some problems. I have these square roots in the denominator. I don't like them. So I want this term to be without square roots, to be an easy term. And then the point is, if I want to lower bound this, I can use the ratio of these. Okay, and so this one will look like what I want to compare it to, and this one will be easy. That's the goal. Okay, so any ideas? What should I make the question mark, and what should I make P and Q?
Well, P is obviously 2.
2/3, right? 2/3. It should
Oh
be
yeah,
a
we're
weight, but
using,
yeah.
oh, I
Yeah,
hasn't
it's-
enough mine. I was using the other way of holder on this.
it's the same, but yeah, 2/3, 1/3. So the point is, you want to do 2/3, 1/3. Why is that? Yeah, so we'll make P and Q are 2/3 and 1/3. The point is the 2. Yeah, the point of the 2 is to get rid of the square, right? But then we have really no choice what to put, right? Because now what? So this will have a to the 2/3, and it'll be this. So I think the only choice we have for this question mark is b plus c times a.
Yeah.
Times a.
Times A, yeah.
Right? Times a. We have to put that. There's no other choice. And now what will the inequality be? So this is okay, so now this is by holder. We have the cyclic sum of a over root b plus c times, that's the power of 2/3, times the cyclic sum of b plus c times a to the power 1/3. This is greater than or equal to, and now because of the choices we made, we really on this side we really get just a, right? Because what? Because yeah, we have to the 2/3 we have yeah, so the b plus c and the root b plus c cancel, and then we have a to the 2/3 and a to the 1/3, we get a. So you really have this. So great. So what was the benefit of all this? Well, we have this sort of thing I don't like, right? Because there's a square root we don't want. And we have the desired right-hand side. And the penalty is we just created a new term, but this new term is much better because there's no square root, right? So if I want to finish the inequality, what do I have to do? I want to show now that what? Okay, yeah, let's do it like this. I say cyclic sum of A over root B plus C is greater than or equal to, so, okay. I'm pasting this over here. This one becomes cyclic, let's start A plus B plus C. A plus B plus C cubed. Let's put a square here because, okay. A plus B plus C cubed over, now I have AB plus BC plus AC, just to the power 1, right? And so now I want to show, so this one I don't know if it's true, but I want to show that this one is bigger than or equal to the squared right-hand side. So 3/2 A plus B plus C. Okay. Is that right? Yeah. And yeah, so now, this inequality is much better. There's no square roots or anything, and it looks the way we want it to. And in fact, it's easy, right? Because, well, okay, you cancel the A plus B plus C. Okay, you cancel the A plus B plus C. And then I'm comparing A plus B plus C squared and this guy. But by Muirhead, I know that this one will be bigger. Yeah.
I think the right-hand side, the denominator must
Yeah,
be 2 times
Yeah, 3 times basically.
2 or 3. I think 2.
Oh, you're saying I lost a constant somewhere, right? Yeah, let me just see. Where did we lose the? Oh, we lost the constant here, right? There should be a. Oh, it's yeah, the constant is here, right? So we cubed this guy. So sorry.
Yeah, it's 2 times I think.
There are 2 here? Is that what I should do? Right, because okay, if I plug in A equals B equals 2, I have 27. Yeah, so if A equals B equals C equals 1, I have 27 over 2 times 3. So that's sorry, I'm kind of losing my constants here. Okay, let's just be careful. So we cube this one, we get A plus B plus C cubed. Okay, and then here we have AB plus BC plus, we have twice that, and then we cube it. Yeah, it's okay, right? I think it's okay now.
Yeah, I think it's correct.
Okay. Yeah, so the point is, yeah, when you do the cyclic sum, you get twice AB plus BC plus AC. Okay, good. Yeah, so any questions about this problem? So the trick, what's the trick? The trick is to use Holder with this 2/1 or 2/3, 1/3 weight, and then you eliminate the square root. It's a very beautiful technique, the way this works.
How did we get the last inequality?
Are you asking why how do you
Yeah,
prove it,
yeah.
or why does it have to be this one?
No, this here.
You're asking why do you see why like I got this from here, yeah? That makes sense, right?
1 second. Oh,
Like
yeah,
we want
okay.
to prove this, right? So
Oh,
I
yeah.
have this, and then so I just want to compare it to this.
Yeah, okay.
You see, yeah? It's just a thing that has to be true if I want to use this technique. But then you need to actually see if it's true, right? Like it could be possible that, this step was way too weak and
Yeah.
this inequality is no longer true, but it works. And it works sort of by inspection, right? Because how do we do? We cancel the A plus B plus C. That was the point of getting A plus B plus C here. And then you just want to compare what? You want to compare A plus B plus C squared is bigger than or equal to some constant times AB plus BC plus AC. Okay? And I know it's going to be true because, well, first of all, I know I'm going to have the correct constant because everything has the correct equality case, so I know my constant will be correct. And also, I know this will be true by Muirhead, right? Because when I expand, I have A squared, B squared, C squared, and then some AB, and here I only have AB, BC. Do you see, yeah?
Yeah, okay.
Okay. All right. So now, so in these arguments, sometimes I sort of, well, you see, I'm making mistakes with the constant. The reason I'm making mistakes with the constant is because I'm not worrying about the constant. Because I know the constant will always be correct because every step I do respects the equality case. So I will never have a problem with the constant. The problem I might have is the direction of majorization might be wrong. Okay, so that's what you have to watch out. Okay, so now let's do, what was the other Muirhead example? Sorry, polar example. Okay, so let's look at this one. This is a nice one. So, so is this the one I wanted to do? Let me make sure. So the next one I wanted to do was actually I want to do something. I want to do this one. Yeah, this is a good problem. So all right. So let's do this one. So and yeah, of course, ABC are greater than 0, and whatever standard assumptions, right? So now it's a little bit weird because so you can imagine, okay, what will I try to do with well, I'll try to write something like A over root A squared plus A squared plus ABC. So if I'll have this, the power of P, and then I'll have something I don't really understand. I'll have to figure out to the power of Q exceeds. Now here I'll have A over square root of A squared plus A to BC to the power of Q and question mark to the power of Q. Now, you can try to get this to be 1. Like if I first look at this problem, I would say, okay, maybe I want to make this one 1, right? So if I want to make it 1, what do I have to do? I have to do exactly what? I have to make it P equals 2/3, Q equals 1/3, and then the question mark is exactly A squared plus A to B C divided by A squared, right? Okay. That makes sense. So then I would get exactly 1 here. But
why
this
don't we just let B equal Q equal 1/2, and we have the question mark be the inverse of A over square root of A squared plus 8BC.
yeah, so we can also do that. And Well, okay, but then you'll still have square roots here, right? Then the question mark will still have a square root. You see, yeah? If I make p equals q equals a half, then it's just they'll have a square root. But yeah, let me just okay. Well, you were suggesting I have p equals a half, q equals a half, and question mark is just the reciprocal of this, right? But now, then, what is the penalty? I have to work with this term, and that's not very much better. Also, I think the point when you write it, what happens? Both of these techniques won't work. You'll see that what you end up having to prove is false, and somehow the reason is you didn't this yeah, it just wasn't okay. Let me maybe I'll just write it out and see what happens, right? So if you use this idea, it just doesn't work. Like we can see what happens. So yeah, so if you do that, this becomes basically 1, and this one becomes, it's a decent expression. It's something like 3 plus symmetric cyclic sum of HBC over A squared. But now you want to upper bound this. That's what the problem will be. This will be what you want to show. Does that make sense? If we use this technique, if you want to show this is greater than or equal to 1, you have to show that this is less than or equal to some constant, right? Does that make sense?
Yes, but it could not be bounded by any constant.
Yeah, but this is false. This is just false by Muirhead, right? This is 1, 1 minus 2. This is 0, 0, 0, right? When we look at the basically what will happen, you'll cancel this guy. You'll get 1, 1 minus 2 and here we get 0, 0, 0. So it's the wrong direction. So the point is, if you do this, it's just too weak. Like this holder is just too weak. You have to do something better.
Does the inequality get stronger the bigger the difference between P and Q is?
Okay, this is a good question. So I think the answer is no. You should think of P and Q as weights. So it's kind of like asking, is AMGM stronger when you make the weights further from uneven? I don't think so, right? No, it doesn't. In power mean, as you make R and S further apart, the inequality becomes not strong, it becomes weaker, right? Because it's true, it becomes sorry, what am I saying? Yeah, if R and S are really close, it's a very strong inequality. If R and S are far apart, it's a very weak inequality.
Yeah.
Right. But here, it's P and Q are not really playing that role. I don't think so. But okay, on the other hand, maybe I'll make a comment about this. What you're saying is kind of true, because what happens when I look at x1 plus xn holder compared to this? Is that what I meant to do? Yeah, okay, it's like this, right? So this is power mean for I wrote holder where one of the sequences is 1, and I deduced power mean for R equals 1 here and S equals P. So in some sense, you're correct. If I make P and Q closer together, it does become stronger. It depends how you look at it.
Okay.
This comment made sense, yeah? About this.
Yeah, yeah, I think so.
Okay. All right. Anyways, the point is, if we want to use holder here, we have to do something a little bit better. So, the idea is, okay, you don't have to get exactly 1 here, okay? Because whatever you get here, the comparison will be between holder will tell you this is greater than or equal to the ratio of these two. So as long as both of these are okay, I'm happy. So the idea is we still keep P and Q are 1/3. We still keep these as 1/3, but now the question mark is what? Well, we still want to have a squared plus a to bc because we want to cancel this guy, but now times a. Okay, times a. Because now what does holder become? It becomes, yeah, so then holder becomes cyclic of a over square root of a squared plus 8bc. So here's our bad term. And here we have something not so bad. We'll have still 2/3. We'll have a squared plus 8bc times a. It's not bad. And here we'll have what? So this and this will cancel. And then we have a to the 2/3, a to the 1/3. We just have a. So it'll be a plus b plus c, like this. Or if you want to keep the same notation, we can write cyclic sum of a, like this. And now, it's okay, right? So if you want to lower bound this, we have to lower bound the ratio, and these are not so bad, right? Like it becomes, so remember, we want to show this is greater than or equal to 1. So what we want to show is that a plus b plus c cubed is bigger than or equal to the cyclic sum of a squared plus abc times a, which of course is a cubed plus b cubed plus c cubed plus 24abc. Which is true by Muirhead, right? You cancel the a cubed, b cubed, c cubed, and you're just left with, on this side, you're left with 2, 1, 0, and here you're left with 1, 1, 1. So it's true. Does it make sense? Do you guys follow the solution?
Yeah, but what was our initial idea to simplify the expression?
Okay, so the idea was I wanted to get rid of the square root, right?
Yeah.
So I want to, well, I have to make this one of the terms in holder. So, or this has to be one of the terms in holder. So I put that here. But then the question is, what do I put here and here? And so the very first idea, which didn't work, was to make this 1, right? So we match this. That's too weak of an idea. We need a better idea. So yeah, so the point is we make it so both of these, neither of them is 1, but they're both manageable. So the point is, okay, we want to cancel the square root, so we have to pick p equals 2/3, q equals 1/3, and put question mark as a factor of a squared plus abc. But then the idea is, what do you put after that factor? There's something here, right?
Yeah.
And the point is, whatever you put here, well, we want it to match with the a to the 2/3, right? Here you have a to the 2/3, so it's natural to put a to the 1/3.
I see.
Because then you'll get a complete a here, and here I still have polynomials, so it's okay. Does that make sense?
Yeah.
Yeah.
Is it mostly the case that the left-hand side is one of holder's terms?
Yeah, you always, so what are you doing when you do holder? You're saying, okay, I have this term. it has something I don't like. It has a fraction, it has an exponent, it has a square, something I don't like. I want to replace it by a ratio of two things. In order to do that, this thing has to be one of the Holder terms.
Yeah, but can't it be the case that the right hand side is the difficult one?
Yeah.
So we work backwards.
Okay. Okay, so you're saying we have a difficult term and you're deciding whether I put it on this side of Holder or this side of Holder.
No, I'm
That's your
saying
question.
the initial inequality that I have to prove, the
Mhm.
left-hand side is normal to deal with, but the right-hand side is the one with the square roots and stuff. So are there problems where
Yes, so there are, and okay, think of it like this. It's not like I really cared whether this was on the left-hand side or the right-hand side. I had this term, I wanted to fix it. But the question is whether I want to upper bound it or lower bound it. I want to lower bound it, right? So I have to come up with a Holder argument where this term is on the left-hand side. If, on the other hand, I wanted to upper bound this term, I would want to come up with a Holder argument where I put it on the right-hand side.
yeah, I wanted to see an example of that.
Let's see if I have one. So okay, let me see. Maybe I have some in my notes. I think one way to think of it is, yeah, maybe I'll do this example. I think the answer, yeah, okay, let me do it. Maybe do the following thing and you'll kind of understand what I'm thinking. So let's look at this example. So here, neither of the terms are that bad, but you can still use Holder. Think of it this way. If you can always bring all factors to the left-hand side. So if I have something bad on the right-hand side, I can always bring it to the left-hand side. Maybe that's something. No, but that's not okay, maybe that's not the point. Yeah, I think Abdullah right now, actually, I don't have a good example for you. I don't really have a good example.
Okay.
Yeah, I'm trying to think if there's any kind of something. Maybe there's some kind of canonical
But
example. I'm not sure.
there are problems where I have to do this, right? Like you upper band with Holder.
Yeah, but right. So right now I can't think of a good example, but maybe there are, right? But somehow, we don't like, okay, in this one, what we do here, like even here, right? Like what we do, like the first step in solving this problem is to write it like this. Okay, like it's but one could imagine trying to use Holder to like maybe get rid of the square here. I don't know. I'm not sure. Maybe there's something. Yeah. I don't know. I don't have a good answer. Yeah, I don't have a good answer. Maybe I'll think about it. Yeah, it's a good question. I don't know. Okay, but anyway, let's talk about this inequality here. So yeah, so for this inequality, the reason I wanted to include this example is because it illustrates a version of Holder where you can, yeah, so Holder was what? It was like you have P plus Q equals 1, and you can say A1 plus AN to the P, B1 plus BN to the Q exceeds this, right? But actually, you can generalize this a little bit more. For example, I can take 3 sets of variables. So let's say I have A's, B's, and C's. Okay, and I add additional weight R. So now the condition is P plus Q plus R is 1. Yeah, that's the condition. And of course, all of them are greater than or equal to 0. So then Holder is still true. I just have to write like this. So I want to point out like why this is interesting. So first of all, the statement makes sense, right? Like what the version of Holder here is.
Yeah, we can also just use AMGM to prove it, right?
Yeah, the proof is exactly the same. It's again by AMGM, right? Like you scale everything down to the sum is 1, and then you have to show that now the point is this is less than or equal to you have A1 P A1 plus Q B1 plus R C1 is greater than or equal to this, right? It's the same argument. Yeah. It's the same argument. You scale them and then you do this. Yeah. So
do Holder
sorry?
does Holder holds for like a number of variables bigger than 3?
Yeah, 3, 4. I mean, it's the same argument. You take each, it's homogeneous in every set, right? So you scale each set so it's sum 1, and then you just apply weighted AMGM with as many weights as you want. So it works. So you can have A1, A, B, C, D, all the way to like Z or whatever. You can have as many as you want. It makes sense, yeah. Kam, you understand how you would prove it, right?
Yeah, using AMGM.
Yeah, exactly. Yeah. It's the same argument with weighted AMGM. So, okay, now I want to sort of say, if you have some, so here kind of the problem, it's okay. Here what's happening is we have a product of 2 terms, and it's not like we have to guess or anything. We kind of just, it's given to us. So there's 2 ways you can analyze this with Holder. You know, if I just keep it as 1 over A times B plus C times A plus B plus C squared. If I just keep it like this, then it's a little bit unnatural because the only analysis I can really do with Holder is I can say, yeah, I can say like this to the 1/3 times A plus B plus C to the 2/3 is greater than or equal to sum of sum of what? Sum of cyclic of 1 over A times B plus C times A to the 2 times this to the 1/3 times A to the 2/3. it's not you guys see, yeah. So this is what holder would give us. If we just did it if we just use like the version of holder with 2 sets of variables, this is really the best we can do. Right? It's just, yeah, I mean, if you just directly apply holder, you get this. It's not, and I don't know, this is not particularly, I don't know if we've improved the situation. Like, I don't, because then what? Then we would have to show that this is more than 27/2, and I think that's false. Is it? I'm not sure, actually.
You can solve it without the other version of holder that doesn't require P plus Q to be 1.
Well, you mean with this, with the three set, right?
Yeah, we can just put that
Yeah.
which one was this? Problem 7? No,
Yeah.
8. Yeah,
Yeah,
we
so-
can do multiplied by the reciprocal of it, and we just show that 9 is bigger than 27/2 plus A multiplied by A plus B plus C squared multiplied by the cyclic of A multiplied by B plus C.
Yeah, so exactly. So this is the trick here is, this is kind of, I think it's too weak. Like I think this ends up being false. So the better thing to do is you look at this, we start with this form. And now what? And now yeah, so now we have, we start with, we do holder, but we do it better. We say the cyclic of 1/A times B plus C.
Multiplied by
We
its
have-
reciprocal.
Yeah, we separate them, and now this will be 1/3, 1/3, 1/3, and the trick is you just do A and you do B plus C, right? Because you can really just make this here 2A, 2B, 2C. Like, okay, well, maybe I'm saying it because we can do it like this. You can say this one is cyclic sum of B plus C. The same. This is just twice A plus B plus C. But now the point is, it cancels perfectly. Does it make sense? Like you just get this, you just get 1 here.
Yeah.
So it's very beautiful because usually when you do this kind of like, how does holder get rid of fractions? It's like you use one term to cancel the fractions of the other one, yeah, but that doesn't quite work here. But what you do is you just split this A plus B plus C squared into 2 things, and each one cancels one of the factors in the denominator. It's very nice. Okay. Okay, so any questions about this?
So the third term was 2 times the first term, or
Yeah, it's twice A plus B plus C, but it kind of doesn't matter, right? It's the factor of 2.
Yeah, we just take the 2 from the right-hand side.
Yeah, like it's why we have in the answer we have this 2 here. Like you'll cube everything, right? So when you cube everything, you'll get cyclic sum 1/A times B plus C times A plus B plus C squared times 2 is greater than or equal to 27. You get what you want. And one thing is, maybe this is what you're trying to say, Abdullah, is this was not an illegal thing. As in, this still respects our equality case. Because what is the equality case for holder? It's the ratios are all the same. So the equality case would be when the ratio of A to B to C is the ratio of B plus C to A plus C to A plus B. And this contains as a case A equals B equals C. So we still respected the equality case. Does it make sense?
Yeah.
So it's a completely valid thing to do. It's totally okay. Okay, so okay, we did a lot of holder and how about this? So I have here some solutions to the other problems. So yeah, I won't go over any more of the other holder problems. They're all very nice, but you can yeah, you can think about them and then I'll send the solutions. We have half an hour now. I do want to mention Janssen. Yeah, I want to talk a little bit about Janssen's inequality. But before you move, the way to learn how to use holder, you really have to do like, 20, 30 examples. And so and you can read the solutions I write, and then also I'll link Evan Chan's handout. But like once you see like 20, 30 examples of holder, you'll understand like how to really use it. Okay. But you really have to study the examples. You have to understand like for each one, how did I come up with that step? Okay. So any questions before we move on to Janssen? Yeah, okay. Yeah. All right. So let's talk about Jensen's inequality. But okay, before we go on, like, using holder is like some kind of like really beautiful art. Like you have to like really look at some like really nice examples, but it takes time, but everyone can learn how to use it. It's really very nice inequality. Okay, so let's talk about Jensen's inequality. So let's give the statement first. So if f is let's say from R to R, okay. So R to R is a convex function. So I'll explain what this means. Then for x1 or xn, these can be any real numbers now. Doesn't have to be positive, whatever. Yeah, so then f of x1 plus f of x2 all the way to f of xn over n is greater than or equal to f of the average, like this. So what's saying here is the average value of the f's is greater than or equal to f of the average value, if f is a convex function. So an example is like f of x equals x squared. It's and this is then it's saying x1 squared all the way to xn squared over n is greater than or equal to x1 xn all over n squared. Okay. And this is just a version of power mean with yeah, so this is just, I mean, it's power mean with r equals 2 versus r equals 1. This is what's going on. You move the square root over to this side, and then it becomes power mean. So the way to think about Jensen is it's saying that yes, here's a remark. If we fix, yeah, so suppose we're in a situation where we fix x1 plus xn is some number s. So you have x1 through xn, and somehow if you fix the sum as s, how to minimize f of x1 plus all the way to f of xn. And so, for example, in this case, like if I fix sum, how do you minimize the sum of the squares? And it's saying that the minimum occurs when all of them are equal. So minimum, so Jensen says minimized when all are equal. Okay, x1 equals xn equals s over n. That's what Jensen is saying. Does it make sense? That's sort of what the idea is.
Yeah, it makes sense.
Okay. So before we prove it, or so before we use it in some example, I want to actually give the proof. So but before I prove it, we have to understand what does it mean when we say convex function. So yeah, like we have to understand what really does it mean when we say a function is convex. So for example, let's consider the function x squared. So one thing we can do, we can graph it. So x versus f of x, and it looks like this. Something like this, right? So in general, a convex function, what does it mean? It's a function where whenever I have 2 points on the graph, I consider the segment that goes between them, it completely is above the graph, right? So an example that's not convex is if I have something like this, right? Now, if I go from here to here, there's this portion that lies below the graph, right? So convex means that if I take any 2 points on the graph, the segment between them is completely above. So I can say it sort of algebraically. So maybe you can call it a definition. F is convex if we take x less than y, and we take t, or let's call it w actually. W between 0 and 1, then f of x times w plus 1 minus w times f of y is greater than or equal to f of wx plus 1 minus wy. Okay, so yeah, so what do I mean here? So let's say here's x and here's y. So where is this wx plus 1 minus wy? So it's somewhere in between. It's some weighted combination, right? Remember we talked about weighted combination last time. So it's some weighted combination. So okay, so here we have x comma f of x, and here we have y comma f of y. And what we'll have here So we'll have, here is wx plus 1 minus wy, and here we'll have, basically the point is this y coordinate here is this number. Yeah, so maybe I can draw some color. So this here, the height is this. But on the other hand, if I go here, like I look at, so if I go here, this is equal to this. Does the picture make sense?
Yeah. So the left-hand side is just the y coordinate where the line between x and y intersects.
Yep,
But
exactly.
yeah,
And the right-hand side is where the graph intersected.
yeah,
So when we give this definition of convexity, what we're saying is if I take any 2 points on the graph, the line lies above the curve. The line segment. I can't go this way. That doesn't work. But the line segment lies above the curve. Does that make sense?
yeah.
Like that's the definition of convex. Now there's another. Yeah.
It's if and only if, right?
Well, this is a definition. I don't know. It's not like what do
So
you mean
you
by
don't-
if and only? You want to think about derivatives, right? You want to compare it to. Are you trying to compare it to something with derivatives? Is that?
No, I was just like because it's written if not if and only if, but yeah, since it's a definition.
Oh, what do you mean? Oh, you mean over here? If you mean here?
Yeah.
Oh no, what would you mean if? What if and only if mean, right? I'm saying like if it's convex if maybe I mean if for all, right? Like if for all x, y, I mean something like it's a definition, right?
Yeah.
Yeah. It's not if and only if, like if I I don't know, like I don't know, I don't know what the only if would even mean here, right? Oh, are you saying that if I go beyond W equals, yeah, maybe, I'm not sure. But yeah, I mean, intuitively, the definition is, any 2 points, the segment lies above the curve. Now, how do you tell if a function is convex? So, okay, in some cases you can graph it like x squared, great. Also, some other, very popular convex functions are like e to the x, right? Like e to the x is convex. You can graph e to the x. It looks like what? It looks like this, right? Where there's like some kind of asymptote to 0 here, right? So it's certainly true that if I pick 2 points, the segment lies above. But in general, is there some condition? So maybe I'll just state a theorem, which you're welcome to use on IMO, which says that if f is twice differentiable, so it has a second derivative, then f is convex if and only if f double prime of x equals 0 is greater than or equal to 0 for all x. So what we're saying is, what does it mean, f double prime? So f prime is the derivative, it's the slope. So f double prime, so okay, what this is saying that the derivative is increasing. So as you look at the slopes of the tangent lines, they're increasing in x. That's what this means. And intuitively, it makes sense, right? Like if I want to guarantee that any segment lies above the curve, it should be that as I go along the curve, the tangent lines are getting more and more sloped. Does that make sense?
Yeah.
Yeah, we actually learned this at school.
Okay, excellent. So the one thing I want to point out is you have to be very careful. These aren't equivalent notions. So let me give an example. I don't know where to give this example. So the example is consider the function f of x equals absolute value x. So what does the graph look like? It looks like this. This is convex. Anytime I have two points, the segment is completely above or on. In this case, it's on. That's okay. On or above the curve. So f of x equals absolute value x is completely convex. Okay, but it's a little weird because it's not differentiable because there's a singularity here, right? Okay, so if your function is not differentiable, you can't really use this criteria. You just have to check by hand. But anyways. Okay, so I hope you understand the difference between like this and convex. They're not exactly the same thing, but they're related. Okay. Okay. So any questions about convexity? Okay, and concave means the opposite. It means that like if the segment is completely below. Okay, so that's and you can check like okay, so it's completely same. Okay, so now let's go back to this. So Jensen says that if you have a convex function, then and this is true. Actually, I want to state something a little bit more. I want to state the weighted version of Jensen because I think maybe it's a little bit more easier to understand. So in the weighted version, instead of just taking average here and here, you take weighted average. So in fact, there's a weighted version which says that if I have weights that are non-negative and I have that sum to 1. Okay, maybe I should use a different color when I'm talking about the weighted one. So weights in red. So if I have weights that are non-negative and their sum should be 1, okay, then it's still true that I take like this, the weighted average here, and also I take the weighted average here as well. Right? This is still true. So one thing I want to point out is the n equals 2 case. Right, so if I just have W1 f of x1, W2 f of x2 in here,
Yeah, it's just
it's the same thing as the
yeah.
Exactly, it's the definition of convexity. So it should tell you that Jensen is, it's very close to the definition of convexity. So what is going on with Jensen? Let's now I give the proof, but you'll understand it's almost obvious. Like once you understand what it's really saying, it's almost obvious. So yeah, I give the proof now.
Yeah, what it's saying is that for any 2 points that the line between them is above the curve.
Okay, good. So that's the n equals 2 version of Jensen. So now let's talk about the higher n, right? So the higher n, we want to say that the weighted, the weighted sum. So W1 f of x1 plus Wn f of xn greater than or equal to f of W1 x1 plus all the way to Wn xn. So this is the weighted version of Jensen. So what it's saying is, what do we do? Like, oops, that's not what I want. We have all these points, right? So x1, x2, xn, like this. So what you do is you look at this shape, I don't know, whatever, and maybe I didn't even draw the shape. What we're doing is we're taking a weight. See, instead of taking the segment between 2 points, you're taking the weighted combination of the points on the graph. Remember, we talked about this last time. Like if you have a bunch of points and you have weights that add to 1, you can always take a weighted combination. Okay, so I take this. I have all these points, and I take a weighted combination. That's some point here. Okay, and so what are its coordinates? Its coordinates are, well, its x coordinate is w1, x1, all the way to wn, xn. And its y coordinate is w1, f of x1, all the way to wn, f of xn. Okay, now we know the weighted combinations, they always lie inside of this convex hull, right? So in particular, this thing, it lies, inside of this convex hull. But moreover, it lies above the corresponding point on the curve. So this green is the left-hand side, its y coordinate, and this red, though, is this one. And so since the green lies above the red, you have Jensen's inequality. Does it make sense? Do you guys understand this argument?
So well, basically, what we're saying is whatever weights we choose, the left-hand side is going to be in this convex.
Mm-hmm. But that's a true for that's true whenever I have any like that's sort of a geometry fact. That's kind of has nothing to do with
yeah.
But maybe I can elaborate a little bit, right? So that's a very important thing. Like, this is sort of the idea behind like barycentric coordinates or something, right? Like if I have 3 points in the plane, I don't know, and I take their weighted combination, right? Any weights. Okay, so let's say if I do it, it's like 1/2, 1/4, 1/4. It's always going to lie inside the triangle. Why is that? Because the way you can take, okay, if I want to do 1/2 A plus 1/4 B plus 1/4 C, I can write it as 1/2 A plus 1/2 of 1/2 B plus 1/2 C. So this one lies between B and C. It lies on the segment here. So then this one lies on the segment from here to here. Does that make sense?
Yeah, I see.
So like anytime I have any number of points, so yeah, maybe here's a lemma. You can sort of maybe prove it. And so W1, so if I have any points like P1 through Pn in the plane, so P1, Pn in the plane. I don't like to call it arbitrary, let's just call it the Euclidean plane, right? So now if I have any combination, convex combination, so they're all positive weights and all of them are they sum to 1, right? So if I want to write W1 P1 plus all the way to Wn Pn, it's going to be W1 P1 plus 1 minus W1 times some weighted combination of P2 through Pn. Okay. Like where the weights will be like W2 over 1 minus W1, W3 over 1 minus W1, all the way to Wn over 1 minus W1. And these have to sum to 1. Okay, so sort of by induction, you're always going to stay inside of the convex hull. Does the proof make sense, Abdullah?
Well, why does this mean that we're inside the convex hull?
So it's by induction, right? So here I have P1, and then I have P2 through Pn. So I know the weighted combination of P2 through Pn lies inside of.
Yeah, I see.
That makes sense. Yeah. So the key fact is these new weights all sum to 1, right? Because what is this? The sum here is well, you see the sum is.
So we can induct this because they sum to 1. Yeah.
Yeah, exactly. So this is the great thing about convex combinations, right? They stay inside of the convex hull. And yeah, so we apply that here, and what we see is that, this green point must be above the curve because it's inside the convex hull of all of it. And that proves Jensen's inequality. Yeah, so it's a very, I mean, it's it's a very nice and intuitive inequality. It's really a graphical thing. So let's talk about a little bit how to use it in an Olympiad setting. So, where did we go? It's here, right? So, yeah, here it is. So the biggest drawback to Jensen's inequality is that it's an inequality about single variable function. So yeah, so what does that mean? So an inequality about a single variable function. So you want to apply it to a situation like this, fine, because we're just using x squared. But what if we wanted to do something like what if we wanted to prove, for example, AMGM using it? Can you do it? Let's see. So I'm going to show x1 plus x2 plus xn over n is greater than or equal to the nth root of x1 xn, right? There's no like, how can we apply Jensen? We have some kind of compound function. This is not a single variable function, no matter how you look at it. It's a multivariate function.
Oh.
Kareem, do you have an idea?
Can we use e to the power of x1 plus x2 and all this?
Oh, okay.
So,
So if we take e to the power here,
or
well,
e to the
now
power
if
of
you
alpha 1 equals x1, for example.
I think you mean you want to use log, right? You say e to the power of alpha 1 equals x1, which means alpha
Yeah,
equals
and
log of x1.
we
So let's use log. Yeah. So this is the key. So whenever you want to use Jensen in a situation with a multivariate function, you have to do something clever. So in this case, we'd use log. So let's take log of both sides. Can we do that? Yes, we can, because in this case, we assume that x1 through xn are all bigger than 0, right? So then you have a positive number on each side, and whenever you have a positive number, you can take log. Okay, so it's okay. If we take log, this becomes log of x1 plus that plus xn over n is greater than or equal to 1 over n times, let's maybe write it in a little bit of a better way. Let's write it as all over n log of x1 plus dot 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 plus log of xn. Okay. Log means log base e, but okay.
yeah,
So
and log is concave, so we
yeah,
get our
but so log is concave. So this actually follows directly from Jensen, right? Because you just have it's concave, you flip the inequality. Yeah. So by the way, so you guys know why intuitively log is concave, right? So when I graph it, right? So e to the
yeah,
x
we
is
just
convex, and so log will be concave because it's the reflection over y equals x. E to the x is convex, log is concave. Is it okay? Or you can take the derivative. Well, the derivative is negative, is you get 1 over x and negative 1 over x squared. But yeah. Okay. So any questions about this? So now I want to go through and I want to see how many of these problems we solved with Holder can actually be solved with the Jensen. And I think maybe almost all of them. Let's look. Yeah, so let's go back to the problems we solved. Start with this one. Can you solve this with the Jensen? So I don't know. It's a little weird, right? There's like I don't know what to do with any of this stuff, right? Like there's they're all very multivariate functions. So can you solve it with the answer? So the trick is if you want to apply Jensen to a homogeneous inequality, usually you have to dehomogenize. Okay, so if you want to solve this with Jensen, so let's take this inequality and let's see if we can copy. That's not even the one I wanted. Is it? I wanted a different inequality. What we were talking about? We were talking about this one, right? Okay. Sorry, I don't even know what happened. I'll just write it here. So the point is you want to solve this inequality with Jensen. The trick is to dehomogenize. So we say A plus B plus C equals 1. And we can do this because it's homogeneous. When you scale A, B, and C by the same amount, both sides scale by the same amount. So you can put an assumption like this, and it's okay. But now what does the inequality become? It becomes cyclic sum of A over square root of B plus C is greater than or equal to square root of 3 halves. But instead of writing B plus C, let's write 1 minus A. And now the problem becomes minimize, right? So we f of x is x over root 1 minus x, and we want to minimize the sum of f of x subject to the constraint on the sum, which is exactly what Jensen is. So we need to understand if this is a convex function. And I won't do the calculation, but you can actually check this is convex. So this problem it follows it's a direct consequence of Jensen because this function is convex. Yeah, so let's just do some sanity check. So why do we think it's convex? Because okay, it's well, okay, first of all, we need to think about the interval x between 1 and 0. That's what we care about. And so there, yeah, so at 0, at 1, it's infinity. And I think it just grows like this. We have to check. But yeah, you have to check that it's convex, but I think it's convex. Yeah, there's no inflection points in here. You have to check. You have to take the derivative and check, but it's true. And it works for other ones as well. Like it works for this one. So yeah, maybe this one I explained. So where did it go? So for this one, you can put a constraint. So you can put the constraint A plus B plus C equals 1 because it's homogeneous. You can do that. And then it becomes show that the cyclic sum of 1 over A times 1 minus A is greater than or equal to maybe it looks like 3. I think it's a little bit better for the let's do 3 instead. Okay, so
but why can we set A plus B plus C? Why can we do that?
It's homogeneous, right? Do you remember when we proved Cauchy-Schwarz, right? Or Holder? We assumed the sums are 1.
Yeah.
And so it's the idea. The point is, if we scale A, B, if we scale A, B, and C by the same number, both sides of the inequality scale by the same amount.
Right. So if we prove this for 3, we prove it for any. Yeah. Okay.
For all, yeah. I mean, maybe the formula you should say, okay, let A prime, B prime, C prime be like A over A plus B plus C times 3, and then 3A over A B over B, like this, I think.
Yeah.
And then, yeah, it's true. Okay, so, yeah. And so this side will become 1/2. And yeah, and you want to show it's minimized when they're all equal, and that will be 1. Yeah, okay. Sorry, so it'll be 3 here, not 3 halves. Okay, and this, yeah, you can sort of see this is convex, right? Because what does it look like? There's asymptotes at 0 and 3, and so I guess it'll look something like this, and so it'll be convex. And you can check with the derivative. Yeah, so I think that's really all I wanted to say about Jensen. Yeah, there's anything else I wanted to say? Okay, maybe I give one more example of a problem you can solve with Jensen, which is maybe you could do it with Holder. I'm not sure, but I don't know if you can do it with Holder. Okay, I'll show the problem and then we'll talk about it. So the problem is yeah, so you have A, B, C are positive, and I have the constraint 1 over A plus 1 over B plus 1 over C is equal to A plus B plus C. So it's inhomogeneous inequality. I give you a constraint. Prove that 1 over 2A plus B plus C squared plus 1 over 1 second, my pen disconnected. I don't know what's happening. Let's just say cyclic sum. Okay, cyclic sum of this is more than or equal to, no, less than or equal to 3 over 16. Oh, so actually, Abdullah, here's an example of something where you might try to use Holder. I don't know if it works, but you might try to use Holder to clean up this term. Maybe you replace it with something a little bit easier to use, because it's on the other side, the less than side, right?
Yeah. Okay.
So yeah, but I don't know. So there might be a Holder solution. I'm not sure. I have to think about it. Okay, so how would you use Jensen here? So the first thing I would do, this is an inhomogeneous inequality. I would homogenize it. So the first thing you do with this problem is you homogenize. And the cleanest way to homogenize, I think, is there's a -2 power here, so you can make this -2 power by replacing with the ratio. You homogenize and it becomes 1 over 2A plus B plus C squared is less than or equal to 3 over 16, 1 over A plus 1 over B plus 1 over C, all over A plus B plus C. Okay. And now this one has no constraint. So this one, without any constraint, is equivalent to this. So we can actually just forget about the original inequality and just work with this. I think it's better. So now, okay, yeah, I think you can try Holder. I don't know. There probably is a probably is a Holder solution, but I don't know what it would be. I don't know. I have to think of it. I'm not sure how it would work, but I have to think about it. The thing I'm thinking though is that, yeah, I have to think about it. Like somehow it's weird because you want to multiply this by something. Like what you want to do is you want to take like cyclic sum 1 over 2a plus b plus c squared, and you want to multiply it with something that like, will kill all these fractions. But the problem is it's on the wrong side of the inequality, right? So it's not going to work. So I don't know. I don't know if it works. Yeah, I don't know. Maybe you can do Holder. I'm not sure. But with Jensen, it's actually it's pretty straightforward, because what's the idea here? Okay, so we have this homogeneous inequality, but in order to use Jensen, you have to dehomogenize. And the cleanest dehomogenization is to fix a plus b plus c. In this case, let's make it 3. It doesn't matter, but let's do 3. So let's fix a plus b plus c equals 3. So now the problem is cyclic sum of, so now you dehomogenize. We fix a plus b plus c equals 3, and now we want to say cyclic sum of 1 over a plus 3 squared is less than or equal to 3. It keeps happening. Less than or equal to 3 over 16 times 1 over a, let's say cyclic sum of 1 over a. And now, what's the idea? So
maybe we should have 1 over 16.
Sorry?
In the right-hand side, we should have 1 over 16 instead of 3 over 16. Because 3 cancels with 3.
3 cancels 3. Okay, very good. Yes, you're right. Yeah, 1 over 16. And now it's makes sense, right? Because I want, let's remind, so the equality should be a equals b equals c equals 1. And so if that's true, I'll get 1/4 squared is 1/16. So yeah, it works. Okay. So now what? Now the point is, this is really Jensen in disguise. How is it Jensen in disguise? The function is f of x is equal to 1 over 16 times 1 over x minus 1 over x plus 3 squared. Okay, because what we are trying to say, we're trying to say we've fixed the sum, a plus b plus c equals 3, and we want to minimize, right? Minimize then f of a plus f of b plus f of c is greater than or equal to 0. So we're trying, it's the Jensen problem, right? We have a function and the sum is fixed, and we want to minimize the sum of the function. And so if the function is convex, we can just apply Jensen. So then you have to check, and it turns out this actually is convex. That's okay, so check. Yeah, so what did we do here? We did some tricks to really turn this into a single variate function, a single variate optimization problem. Does it yeah. Does it make sense? Do you guys understand this argument?
Yeah, I think so.
Yeah. Okay. Yeah. Okay, great. So that's what I wanted to explain about Jensen. All right. So any questions about inequalities, Cauchy, Schwarz, Jensen? This will be our last inequalities lecture. Okay. Let's just stop the recording. So